All right. Good afternoon, good morning, good evening, whatever time it is when you're watching this video. Welcome. This is our day two video for our MA 208 statistics course. So we're going to be getting into our the last of our chapter one material. So wrapping up some of this definition material, definitions that we're going to use throughout the course. Um, And then this will give us kind of our building blocks as we move into chapter two, where we start to do some actual mathematics calculations. Okay, so I'm going to go ahead and share my screen here. So share my screen. Here it is. Okay, great. So, all right. Uh, we're looking here on the course schedule. I just want to remind folks that, this is a great page you want to look at on Canvas to keep track of when things are happening. This video is designed for day two, where we will be covering sections 1.4, 1.5, and 1.6. You will also want to note that we do have test one is going to be coming up next week. More information about that will be posted in the announcements later this week. All right, so be on the lookout for that as we get closer to test one. That will take place on the date shown in the schedule here. Okay. So we're going to wrap up chapter one today. We have our participation question for today. We'll come to this here in a little bit. Let's just go ahead and jump into the textbook. So section 1.4, we are talking about types of data, which we actually had already touched on this in the last video, where we talked about how the data we collect can be numerical, meaning it's a number, it's some kind of numerical data which we record. It's a number which we can add or subtract, or we can take an average with it, so on and so forth. Or we can have categorical data, where it's data which we can fit into categories, but it doesn't really have a numerical meaning. Take, for example, we talked about favorite flavors of ice cream, or if we're talking about eye color, that is categorical as it doesn't have a numerical value. So 1.4, just to further highlight this, when we're talking about numerical, this is quantitative. So when you see the word quantitative, you want to think like quantity. If you can take a quantity of something, then you can count it. If you have a quantity of apples, then you have some number of apples, right? Whereas qualitative, you want to think like the word quality, where whatever you're trying to study, it might have a quality about it, a characteristic about it, which is not necessarily numerical. It might not have a number value, like eye color. That is a quality about a person, but it's not a number, right? It's a category that I could try to place a person in based off of eye color. All right. So we have the same distinction here, where quantitative, think numerical. We're talking about numbers. This is information like height or weight, or if I put out a measuring cup outside to measure like how much rain falls from the sky, that is a numerical recording that I am collecting from the outside weather. All right, that's quantitative. Qualitative, which is the same thing as categorical, this is data which is not numerical. So think like color, or if we're talking about a species of animal or species of fish, we could be talking about the brand of car that you drive, right? If you have a Ford or a Toyota or whatever car, that brand of car you drive does not have a numerical value, right? It's a category that can be placed in, so it is qualitative, okay? So we see here in this first example as we're talking about this chemical plant and how it relates to this ecosystem around the chemical plant. Even from this one problem, we can have multiple types of quantitative and qualitative data depending on what it is we're trying to collect. So we read here, the manufacturing plant, they have a discharge of toxic waste material, such as DDT, into nearby rivers and streams. DDT is just some chemical compound, all right? These toxins can adversely affect the plants and animals inhabiting the river and riverbanks, at least depending on what kind of level we're talking about, right? I mean, after all, all throughout the world, there are unfortunately some bad chemicals out there, right? If those bad chemicals in the environment are at a low enough level where it's maybe not as harmful or not as dangerous, then okay, maybe it's at a manageable level. But that's data that someone has to collect to determine are things at a safe level or not. All right, that's part of the purpose of this kind of study. So, the U.S. Army Corps of Engineers, they conduct a study of fish in the Tennessee River in Alabama and its three tributary creeks, Flint Creek, Limestone Creek, and Spring Creek. All right, they have these three different locations. You just want to see, are these locations being impacted? Maybe one of them is, and the other two are okay. But we want to know, well, which one is being impacted, if any of them are. All right. A total of 144 fish were captured, and the following variables were measured for each. So think back to the last video. The population that we're interested in, we're looking at the fish population around this manufacturing plant. Okay. But unfortunately, we're not going to be able to collect data on every single fish that exists around the plant, right? It might not be possible. Some of them might be hiding at the bottom of the river or at the bottom of a lake or something. We just have no way of being able to collect information on every single fish in this population, all right? So we have a sample of these 144 fish. This is taken from the population where we hope this sample can tell us information about the larger population we're trying to study. Okay? And so this is our experimental unit we're trying to study, the fish. But these fish, they have multiple variables that we can collect information for. We can collect, well, where did the fish come from? After all, if I have a sick fish, then I need to know which creek it was in so I can tell geographically where the impact from the manufacturing plants is hitting most. Okay, so where does the fish live? Well, we know they're studying these three different creeks, but this is categorical. This is qualitative. The name of the creek, Flint Creek, doesn't have a numerical value. It's not a number, right? I can't add or subtract Flint Creek. So this is qualitative data. I'm also collecting, well, what kind of fish? After all, maybe some fish are okay. Maybe there only some species are being affected by what's being seen in the waters. All right. So we collect their species. Are they a catfish? Are they a bass? Buffalo fish? So on and so forth. Again, qualitative, right? This is not a numerical value. This is a category or a quality about the fish that I am collecting information. But these next three variables are then quantitative, they are numerical. How long is the fish? Is it a big fish? Is it a little fish? That can maybe tell me something about the age of the fish. If little fish are all healthy, then okay, maybe that tells us that at least younger fish haven't been alive as long or not being affected as much. But if older fish who are showing signs of sickness, then okay, maybe then that tells us that older fish that are around longer are more affected over time, and then eventually they become sick. That then can tell us information, right? So the length of the fish, numerical data. How long is it? This is a number. The weight of the fish. Is it a big fish? Is it a skinny fish? How healthy is it, right? And then lastly, they're collecting information on the DDT concentration parts per million. How much of this chemical, this toxic waste, is actually present in the fish? Is there a little bit? Is there a large amount? Does it seem to be affecting the fish in some way? This is a concentration, which is a numerical value, and so quantitative. All right. The point here is that this is just a single statistical study where we have multiple variables being collected on the experimental units, on the things we're trying to study. And the variables are not necessarily all quantitative or all qualitative. We can have a mix of what type of variables we're actually talking about here. Okay. All right. So that highlights section 1.4. As we turn to 1.5, part of our concern now is, okay, what makes a sample a good sample? We hinted at in the last video that, well, okay, sample size matters. If my sample size is too small, if they only pick out one fish and they look at the fish and like, oh yeah, this fish is healthy, throw it back in, they're like, okay, we're done. All the fish are healthy. They only checked one fish, right? The sample size matters and it determines the reliability of the information that we've collected. If I only look at one fish, it could have just been dumb luck that I just happened to pick a healthy fish. That tells me nothing about the population as a whole. So sample size is one thing that really matters for a good sample, a reliable sample. All right. Another part of what can matter for a sample is where is your information coming from, right? This is super, super crucial, kind of honestly, in all parts of society. When you collect information, where do you get your information from? Is it reliable? Is it trustworthy? Do you expect the information to be true? Or is it more opinion piece where someone is just telling you what they think, but they have nothing to back it up with? All right. So where our data comes from is important. So in general, when it comes to sampling, we have three ways of doing this. First, there might be a peer-reviewed, published source, a published paper from other scientists who have gone and collected data, and they are reporting on what they found, right? A published source, especially when it's peer-reviewed and other scientists are able to check on it to see like, well, okay, your data makes sense, or maybe it doesn't, and other scientists call them out and say, well, hold on, your published results here, you made a mathematical error here, right? Uh, so when it is peer reviewed, it then becomes more reliable. And so that's one place we get information from. The other option is to go out and collect the information for ourselves. And we do this in one of two ways. One, we design an experiment where we are controlling what is happening in the experiment. You take a rat and you place it in a maze. You have control over what is happening to that rat in the maze, right? You're doing a biological study with maybe human patients where you have some new drug that you want to test. Does the drug help cure some illness or not? Well, then you have to do a study, right? You take some people who have some illness, and some of them you give the drug to, but then you also have a control group where maybe you give them a placebo pill, you give them a sugar pill that doesn't actually do anything. But the point, as you are controlling what is happening to the experimental units, in that case, the people in the study, you are controlling who has the drug and who doesn't have the drug. You don't tell them which is which, and then you see from the results, well, do they get healthier? Do they get healthier just because they think it's doing something? Is it just a mind over matter situation, in which case the drug's not actually helping? Or does the drug actually improve the situation? In which case, only the group with the drug should show improvement, where the placebo group should not show improvement then. All right. That is a controlled experiment where um, the researchers have some level of control over the experimental units they're trying to study. An observational study is kind of the opposite from an experiment in this regard, where for an observational study, we're removing the control. We have no control over the experimental units. We're simply observing what they're doing. Take the rat example. Placing the rat into a maze, that's an experiment. I am controlling the environment around that rat. Or if I go out into the forest, I'm walking around hiking, and I see a rat crawling around under a tree, I am observing what's happening with the rat. And maybe I'm writing down some information, but I'm not otherwise controlling anything around the rat. All right. So in experiment, we have control over what we're studying. In observational study, we have no control over what we're studying. We're simply observing them in kind of their natural environment. All right. And so we have this distinction between an experiment or a study. They also have here, as an example, a survey is another case of an observational study where you just go around and asking people stuff. You're not controlling anything about them. You're just collecting information as they report it to you in a survey. All right. So we have this distinction. For a designed experiment, the researcher exerts full control over the experimental units sampled. For an observational study, we're collecting data from these experimental units, but they are observed in their natural setting. We're not controlling their environment. We're not controlling characteristics about the experimental units that we're trying to study. All right. So we have these two different types of ways of collecting data from ourselves if we're not getting the data from a published source. Okay. Now, the concern is what makes a sample a good sample. Ideally, we want a sample to be what is called representative. Consider the Belmont Abbey student population. We have men and women students. We have male and female students, right? So if I'm trying to collect information about Belmont Abbey students, well, then my sample, in order to be representative, should have both men and women. If I go around trying to collect information and let's say I want to find out, well, what is the most popular hangout spot for Belmont Abbey students? Well, if I collect a sample and my sample has 10 men in it, well, okay, that might tell me about where Belmont Abbey male students like to go to hang out, but it tells me nothing about the women and it tells me nothing about the female population in the student body, all right? That sample would be not representative, okay? So for a good sample, if we're trying to say something about a larger population, it needs to be representative of that population, okay? It needs to exhibit characteristics typical of those possessed by the target population. Now, there is some trickiness here, which we'll get into in a moment, but we kind of have this ideal goal of what we're trying to have. We need a sample to be large enough, right? If it's only one person, that doesn't help. The sample needs to be large enough and it needs to be representative. All right, that's kind of our two pieces we're looking for in order to have a good sample, a trustworthy sample. All right. Now, one issue we can run into is possible bias in how do I select people to be in the bias or to be in the sample, I mean. If I go around Belmont Abbey campus and I'm asking different students to be involved in some survey or some study, I might subconsciously be selecting people that like, well, I think that person looks nice, or I think that person looks smart, or oh, that person looks dumb. I don't want to talk to them, right? And I might be subconsciously thinking that, and it may direct me one way or another as far as like who do I ask to be part of the survey, and whether I'm doing it intentionally or not, the way I'm selecting people to be in the sample might be biased, right? Me picking who's in the sample maybe a bad idea, right? So what do we do? How do we get around a selection bias of this kind? We make it random. If we are selecting people randomly from the population, if I go to the registrar at Belmont Abbey, I have a list of all the students. They have student ID numbers, and then I just take a random number generator and I say, okay, randomly pick 20 students from the student body. All right, that randomness is going to help eliminate some of that bias that I might have in how I would select people to be in the sample. All right. Now, randomness does not necessarily fix all of our problems. After all, I could just, by dumb luck, if I randomly pick 10 people, I could just happen to pick 10 male students randomly. In which case, I have a problem where it is not representative. If I want to have both men and women in my sample, well, then my random sample may, unfortunately, sometimes randomly end up being biased. Okay. So randomness does not necessarily fix everything, but it's a first step, right? We take a random sample, we can check, is it representative? If it is, then great. We move on, we can use that sample. If it's not representative, well, then maybe we pick a new random sample. We have it do it again, pick 10 new random people. Um, Part of what helps with this kind of issue, though, is that if the sample size is large enough, then it becomes unlikely for the sample to be not representative, right? I mean, if I randomly pick 5 students from the student body, then sure, it could happen that it would randomly pick 5 men, and then it would not be representative. But if, for example, I pick randomly 100 students, Well, now the chances that all 100 are going to be randomly selected to be all men, that's becoming more unlikely, right? So the larger the sample size with the randomness helps guarantee that, okay, my sample is most likely going to be representative the way we want it to be. Okay? So randomness and sample size together is going to be the key ingredients to what helps us create a representative sample. All right. But there are still some other types of bias that we could run into. So let's talk about the other types of bias. One could be selection bias. That's also like a kind of bias that I was talking about earlier, where maybe if I'm picking who's in the sample, maybe I would be biased in some way. Um, Other types of selection bias may occur when a subset of the experimental units in the population has little or no chance of being selected for the sample. Consider if I have a classroom where maybe 19 of the students are women and only one of the students is a guy, is a man. Um, Even if I'm going randomly, even if I'm randomly selecting, the odds of that one guy being picked aren't super great, right? Even if I randomly select a bunch of times, the odds are unfortunately in favor that my entire sample would be all women. Now, of course, that classroom is predominantly women, but if you want a sample to be representative, well, then I would like that one guy to be in the sample, so I have also a male opinion in addition to the females' opinions. Um, but a selection bias can occur in this regard where if some small subpopulation of the larger population, if it is so small, then it might be hard to pick at it, even if we're doing this randomly. All right. Now, there are ways of getting around that where maybe before we randomly select, we would sort the population. And by sorting the population into different categories or groups, then we ask the computer to randomly select people from each category. That can be a way of forcing it to be representative, um, while still maintaining the randomness that we want. Okay, so selection bias is one possible issue. If a group is too small to select, it might be hard for it to appear in a random sample. We can also have a non-response bias. Now, this is often pretty common with surveys in particular, because let's be honest, you get a survey, whether it's in an email, or you get a letter in the mail that's a survey, or some kind of survey from the school where they want to know your opinion on something. A lot of us don't like filling out surveys. We just don't. We got better things to do. We want to go about our lives and not worry about it. We have a non-response to the survey. All right. So a non-response bias occurs when the results, or the results when data on all experimental units in a sample are not obtained, right? So I send out a survey and, well, a bunch of people don't respond. There is a non-response bias that can occur. All right. Or maybe the people who do respond, if they're like super excited about the survey or whatever it's about, they might be already, because they're excited about the survey, be biased to answer the questions a certain way. In which case, while we have this non-response from some groups, a response can also be a form of bias depending on what is going on with our survey. All right. That can be trickier to avoid. Um, Now, for our purpose of this course, as we continue into later chapters, we're going to be focused more so on the numerical analysis, the statistical analysis, the mathematics behind how do we analyze data, where we're just going to assume that, okay, the data we're analyzing, let's just say that it's representative, that it's a good type of sample. But in the real world, if you are trying to collect data, then these are questions we have to think about in terms of trying to make sure that the sample we collect is representative, that it's random, that it is reliable. Okay. So these are things in terms of the philosophy of statistics that have to be followed in order for your statistics to be meaningful to the rest of the world. All right. Now we can also talk about measurement error. So this is not bias. This is just when someone makes a mistake as they are recording the data. It could be a misplaced decimal point. I have a fish which is, 1.5 pounds, right? But if I accidentally move the decimal point, or if I forget to write the decimal point, then I might write down the fish is 15 pounds. That's a pretty big fish now, right? And so that could be a measurement error where I have collected the data, but the number has been written down wrong, or it's been written incorrectly, or typed in incorrectly. So these are inaccuracies in the values of the data that's collected. It could be numerical, but this can also happen with qualitative. I see that someone has blue eyes, but I'm just kind of absent-minded. I'm thinking about something else. And as I'm writing down their eye color, I accidentally write down brown instead of blue. Well, then I have made a measurement error where I have incorrectly collected data from the experimental unit. So a measurement error is not just numerical. It can also happen with categorical types of data. All right. This can happen in surveys where some error may be due to ambiguous or leading questions, and the interviewer's effect on the respondent. Um, there are other types of measurement error besides just numerical errors, where a number is written incorrectly. All right. Um, so we have this example here where we're talking about web users who are addicted to the internet. So to study this, psychologists designed a series of 10 questions. They're going to take a survey based on a widely used set of criteria for gambling addiction and distributed them through the website abcnews.com. All right. So a total of 17,251 web users respond to the questionnaire. Now, you might already be thinking right away as I'm reading this that, well, there might be a non-response bias here, right? I mean, after all, people who are not addicted to the internet might see that survey and be like, I don't care about this. I'm just trying to do whatever and then go about my day, right? People who do respond to the survey, maybe they're possibly more interested in the internet or they're more excited about the internet. They see the survey and they're like, ooh, I want to do that survey. And so they jump into it. They start answering the questions, right? Now, I'm totally making this up. I have no idea whether this sort of bias is actually happening or not. But part of the challenge with statistics is that we have to ask these sort of questions. Well, is there a possibility for bias? Can we imagine that there might be some kind of bias occurring, even if the question doesn't tell us that? All right. So we continue reading. If participants answered yes to at least half of the questions, then according to this questionnaire from the psychologist, this would label them as a possible addict. The findings released at an annual meeting of the American Psychological Association revealed that 990 respondents, or 5.7%, are addicted to the internet. All right. So, some issues here. We're trying to do a study of the entire population of people who use the internet. According to this, does this mean that 5.7% of people who use the internet are addicted to the internet? Well, we have no idea, right? There could be some bias at play here. It also could be, maybe some people would go to the website ABC News, maybe some people wouldn't. And then you have another type of bias occurring there where, that is possibly dividing the population in some way in terms of who is actually looking at it or who is not. Um, as we identify the data collection method, this is a survey, right? This is observational. They're not trying to control what's happening to these people. They just want to collect information from them that's being reported, all right? Target population, we're looking at these internet users as a whole. But again, these are only internet users which are on this website. These are only internet users who they see a survey on a website and they're like, yeah, I want to respond to that, which a lot of people don't want to, right? Or wouldn't answer a survey on the internet. That's not always something we want to do. It depends on how interested you are in the survey. So this is target population. Are the sample data representative of the population? Unfortunately, we don't know. I mean, on one hand, let's see, do we have any information on the year? I don't see anything on a year here. No. We have no idea if this is representative, right? The people who answered this survey, are they men and women? Are they only all are a majority of them men or a majority of them women? Um, the people answering this survey, because they answered it, does that mean there's a response bias where they're excited about the internet? In which case, they're going to be more inclined to answer a certain way versus people who are not addicted to the internet are probably more likely to have a non-response and say, no, I don't care to do the survey. I don't care that much about the internet. And so we already have the possibility of some kind of bias occurring here. Now, the answer they give here in the textbook, they say that, we don't really have enough information to say whether or not this is representative. But we can say that there is some kind of bias here where we have the respondents are self-selected. They are self-choosing to answer, right? So this isn't a random selection. These are people who are choosing to answer. And then we have the possibility for non-response bias. All right, so we have this example. Um, so moving forward into 1.6, as we're wrapping up chapter 1, part of this concern is the overall philosophy of statistics. What makes good statistics? What makes bad statistics? We want statistics to be trustworthy. We want it to be reliable so that when we find something or when we find some statistical result and we report on it, people are able to trust it, people are able to believe it, and then this overall adds to the knowledge of people in general, right? Um, so there are some things we have to watch out for. And we did talk about in the last video that there are different types of statistics where we can do descriptive statistics, where I'm just trying to describe something. I'm not trying to predict. I'm not trying to make generalizations. I'm not trying to make any kind of inference whatsoever. I'm just literally describing what does my sample show, and that's it. But when we talk about inferential statistics, this is where we have to be very careful with statistics. Because after all, our hope or our goal is to make a generalization about a larger population, right? I want to find out the favorite ice cream of students at Belmont Abbey College. That is my goal, right? I go out, I collect my sample, I'm studying the information. But unfortunately, despite my best efforts, that might not actually tell me about what's happening with the entire population. One thing we have to watch out for, and this is also highlighted by the philosopher and writer H.G. Wells, who stated crude classification and false generalizations are the curse of organized life, which, unfortunately, is something we run into day to day, all through society. We want to try to make generalizations, whether we're talking about a population of people, or we're trying to make generalizations about a model of cars, if we're talking about Fords versus Chevys or whatever. We like to make generalizations. We try to. Maybe it's human nature. Um, Unfortunately, despite our best efforts, when we're performing statistical thinking, this involves applying rational thought um, and the science of statistics to critically assess data and inferences. We're trying to make generalizations, we're trying to make inferences, but we have this fundamental issue we run into. Fundamental to the thought process is that variation exists in populations of data. This is just a reality of population data. Variation is natural in a population you're trying to study. I want to find out, well, how tall are Belmont Abbey students? Maybe I do some studies and we collect some data. We find the average height is like 5'9", 5'9" Does that mean every single student at Belmont Abbey is 5'9"? No, of course not, right? I'm trying to generalize, but the reality is, despite my best efforts, the population I'm trying to study has variation. Some people are taller, some people are shorter. Maybe a majority of the people are around 5'9", but there's always going to be built into the population we're trying to study variation, right? So as we continue into chapter 2 in these later chapters, we'll talk about statistical techniques for, well, how do we measure variation? Do I have a population which has a high amount of variation? In which case, that's very difficult to make generalizations about because the numbers, the data is all over the place. It has very high variability. Other types of data might be more monotone, where we collect the data and there's very little variation, where everything is the same, or everything is the same height, everything looks the same. Um, some populations have a low amount of variation. Some populations have a high amount of variation, all right? But whatever population we're studying, this is just something we have to be aware of as we're trying to make inferences that there may be some natural variation in the population we're trying to study that we have to contend with. Okay? We'll talk more about that as we continue into chapter 2 and so on, as far as how do we actually do that? How do we measure variation? We'll do that later in the course, but for today, our goal is to wrap up chapter 1 here. All right. We have these definitions. We have some examples. So we'll end here for chapter 1, looking at this last example, where we have an article in the New York Times considered the question of whether motorcyclists should be required by law to wear helmets. In supporting his argument for no helmets, the editor of a magazine for Harley-Davidson bikers presented the results from one study that claimed 9 states without helmet laws had a lower fatality rate, um, with 3.05 deaths per 10,000 motorcycles, than those referring to other states that had mandated helmet laws. All right, so he's citing this as evidence, right? Now we can already see, you might already be thinking that, well, is there some bias at play here? This is an editor for the magazine for Harley-Davidson bikers. He might already have his own kind of agenda coming into this, right? He also shows a survey that found of 2,500 bikers at a rally, 98% of the respondents opposed such laws, trying to show evidence like, look, bikers don't like these laws, we need to get rid of them. All right. Again, looking at this survey, is there a possible bias here? This is at a bikers rally. People who ride bikes and wear helmets, are they at bikers rallies? Some of them are, sure. But if they see someone walking around like, hey, what do you think of helmet laws? Do they want to respond? Do they not want to respond? Do certain people of certain viewpoints, are they more likely or less likely to respond? Is there a possible response bias here? We don't know. The information, we don't have enough information to really say what kind of bias might be happening, if any, right? On one hand, maybe we trust 100% what's happening here, but we can keep reading. Based on this information, do we think it is safer to ride a motorcycle without a helmet? All right. Now, it doesn't take much rocket science to realize that, well, wait a moment, people who wear helmets, though, actually are less likely to get hurt in accidents. There are many, many studies that show the opposite of what is being presented here, right? So what's going on? This is an example of where we can see bad statistics at play. When we are presented with information, when we're presented with data, we have to critically think for ourselves, well, hold on, is this good statistics? Is it bad statistics? How do we know? Is there bias at play? Is there not bias at play? Um, as we evaluate this study, we do want to know more about the data that's collected. Is this being randomly collected? Is this self-reported? Is this a person walking around and they're just picking people they want to ask? If this person who has their own agenda is going around and they see people, if they see bikers not wearing helmets, they might go up and ask them, like, hey, what do you think of this law? They are choosing people who are already not wearing helmets, and they might be messing with the numbers because of who they're asking. Versus if they see a biker with a helmet, maybe this particular survey, they're like, let's not ask him. He's wearing a helmet, right? In which case, they have this bias in terms of who are they surveying and who are they not surveying. Okay, so we need more information. Can we actually trust this 98% claim that they're making? All right. Um, so yeah, we got to worry about that. Is it random? Is it not, or is it not random? Um, we also have this study comparing the fatality rate for these states without helmet laws versus states that do have helmet laws. You can notice here they're not comparing all 50 states, right? They just happen to pick these 9 states without helmet laws where it was lower. But are there other states with no helmet laws where it's actually higher? In which case, they're cherry picking which states they want to present to you, and the states they don't want you to think about, they're like, let me not mention that. I'm going to keep that, sweep it under the rug and not talk about it, right? By only presenting what it is they're trying to prove, there may be some kind of bias at play here, all right? So we want more information about the study comparing these fatality rates. Were all 50 states included? Did they cherry pick? So they're only telling you about the states that prove their point. If after all there are 20 states without helmet laws where the fatality rate is higher, well then their whole argument falls apart, right? They're only telling you the piece that they want you to hear. Um, And so, we do have some natural questions here in terms of, is this statistics actually trustworthy? All right. So we have to think about this in terms of the general philosophy for statistics as a whole in general society, um, whether or not what is being presented is reliable information. Okay. Now, this class is not a philosophy class, so we're not going to get so bogged down in these kind of details. For chapter 2 and into the later chapters, we're going to be more focused on the mathematics behind how do we actually do a statistical analysis? How do we calculate variation? How do we determine generalizations? How do we make inferences that are trustworthy? How can I make a claim that would maybe sway opinions, but have that claim actually be backed up by good mathematics? That's what we want to try to do from here to the end of the class. All right. So this wraps up chapter 1 for us in this video. The last thing I want to talk about is our participation question for day 2. So we'll go over to participation day 2, and we have this question presented. A survey with Belmont Abbey College students is conducted asking about what type of car they drive, if they have a car at all. 17 men and 3 women take the survey. First, what type of data has been collected here? Well, we're asking about what type of car, the car brand. Is it a Ford? Is it a Toyota? Is it a Chevy? Whatever it is. This is qualitative data or categorical data. Same thing, right? Qualitative, categorical, same word. This is non-numerical, right? This is qualitative. All right. Lastly, is this a representative sample? Well, there are men and women who drive cars at Belmont Abbey, right? This sample might do a good job of telling me, well, what do men drive at Belmont Abbey? But it's not going to tell me as much about what women like to drive at Belmont Abbey. And so this sample would not be representative of my target population. All right. So for today's participation question, let's see. I should have, oops. Yeah, here we go. Got a text box. For today's participation question, this is qualitative data, and it is not representative. Not representative. Okay? So this will give us our answer for today's participation question. It is qualitative data, and it is not representative. It's not a representative sample. Okay? If you have any questions about anything we talked about today in this lecture video, please feel free to email me, talk to me, come by office hours. I'm happy to help you with any concerns you may have. Otherwise, that's all we have for this video. So I wish you the best of luck, and I will go ahead and close out here. All right. Have a good day or good night, whatever time it is you are watching this video.